All right, I'm going to do problem 2B, or practice B, problem number 2 here in a second, because it's kind of difficult. But I also just want to say one thing about the lecture that I had for momentum, and that was about that trampoline example where I had a person that made a jump on a trampoline of 4 feet. And if they make a jump of 4 feet, we can use the formula we just had a second ago to talk about the difference, right? Meaning the difference between making that jump on the ground, we'll say this is the ground, and then making that jump on a trampoline. Okay, and why one of them is way safer and one of them isn't, and how this relates to the impulse momentum theorem. The impulse momentum theorem is that impulse, or J, is equal to the change in momentum, and I knew I can expand J out to be F times T, and delta P, which is MVF minus MVI. I think I'm just going to leave it as delta P right now, just to prove a point. This person, when they're up here, has a mass, and when they fall this distance, they maybe at the top of the jump, maybe this is the top of the jump, they don't have a velocity, right? So let's say they have VI, and this is their initial velocity, and it's 0. But we know after they fall that they're definitely going to have a velocity before they hit the ground, right? And I could make one up here if I wanted, but I'll just say it's VF and it's pointed down. And the same thing is true right here, that the person, when they get to the bottom, they have a VF and it points down. All right, so what I'm trying to say here then is that if we go back to maybe here, that they are going to have the same velocity in either case pointed down. And furthermore, they're going to have the same mass in either case, assuming this is the same person, right? So if I look back at this formula, I guess I'll expand it out. I wasn't going to, but I think it makes more sense to do that. We know the initial velocity is 0 because we said that right at the top. So I can get rid of this because this is 0. And 0 times the mass is just going to be 0. So I'm left with this formula right here for both cases. And in both examples, this is going to be the same. And the mass is going to be the same because it's the same person. But over here, we see the difference between making a jump on the ground and making a jump on the trampoline, and why the trampoline is so much safer. Because this number, same times same, whatever it is for both situations, maybe it totals 100, right? And I'm just making something up, right? 100 kilograms meters per second. And here we see that there's multiple ways to reach 100. You know, you can have different numbers, right? You could have 100 times 1. You could have 10 times 10. You could have 25 times 4, right? And, infinite number of ways to hit 100, multiplying two numbers together. But my point is that when you make this jump on the ground, the time value is going to be that you're going to experience this force as you hit the ground, right? There's going to be a force upwards, and that time value from the ground of that force is going to be very small. So the ground is going to impart a force to you upwards, right? Because you have the force of gravity in both cases, which is the same, but you're going to receive a sharp force upwards from the ground that's going to be large. So if I was to write this out, I would say for the ground example, right, that of F times T equals MVF, that this number still has to be, or this quantity still has to be 100, and that this is going to be a very, well, we know the time that you experience the force on the ground is going to be very small. And so therefore, to hit 100, this force has to be very large. All right, and that doesn't sound very nice, to experience a very large force. And then you have the example of a trampoline, and now this makes more sense. Why, right? Why it's different, hopefully. You have F times T equals mvf. And once again, this is still 100. But now, in this case, the time that you experience that force, because you can think of it when you hit this trampoline, right? You experience the force upwards over a larger period of time, that this time is larger, right? So I'll just write larger. And then therefore, the force that you experience is smaller, right? Because maybe this time period for the trampoline is over 1 second, and maybe this time period of the ground is over a couple milliseconds, right? So this is on the order of almost being 1,000 times smaller than this time period. So therefore, the force here would be 1,000 times larger, and this force would be 1,000 times smaller. So it is a significant difference. And we see this here with trampolines or airbags or things like that. All right, hopefully that makes sense, this connection between impulse and change in momentum. All right, wanted to talk about problem 2, practice B. And I think this problem is more difficult than other ones. And so I just wanted to bring it up. It says an 82 kilogram man drops from rest on a diving board 3 meters above the surface of the water, comes to rest 55 seconds after reaching the water. After reaching the water, that's tricky. So that means he jumps off the diving board, hits the water, and then takes 0.55 seconds to stop in the water. So that's his time period in the water. What is the net force on the diver as he is brought to rest? Well, if the diver jumps into the water, the net force on the diver to slow the diver down is going to point upwards, right? But the diver is going to be moving downwards. All right, so let's look at that, right? There's a lot going on there, and see if we can do a drawing here. So we have maybe a ladder to a diving board. And some water here. This is not a very good drawing. Okay, something like that. And this person is going to make a dive here, and this height, they tell us, is 3 meters from the diving board to the surface of the water. But then the person is going to enter the water over some distance that we don't know and come to a stop. So it says that the man drops from rest. So the initial velocity right here is going to equal 0. Then they're going to have some final velocity right here, right, which is going to point downwards. But then they will enter the water and then reach some point where their velocity now is 0. And we want to know, what force does the water push upwards with over this distance to cause this slowing down. And so really it's like 2 problems, right? You got the person making the dive, hitting the water, right, at this velocity, and then, or I should say, making the dive, falling through the air, obtaining this velocity, and then entering the water receiving a force upwards from the water and slowing down over some time period, which I think, even though we don't know this distance, we do know that this time is equal to 0.55 seconds. And I think we also know the mass of the person is 82 kilograms. And that won't change throughout the problem. All right. So we want to know, what is this force that the water directs to slow the person down, and then therefore that this force is upwards. And so here signs are going to be important. So we got to call directions, we got to give them positive or negative signs. So let's go ahead and call, I guess, up positive and down negative. That's arbitrary. You could have picked the opposite and would have been fine. All right, so let's deal with this first part here. And there's multiple ways to solve it. We could use K formulas. I think I'm going to stick with energy because we had just talked about energy before. We know that the person right here, before they make the dive, has a height, and then therefore they have a type of energy. And then they're moving right here, right? They're moving downwards. And so right here they have a type of energy, a moving energy. And we're going to energy balance this. That way I can find this final velocity. Well, it's the velocity before they enter the water, but I'm calling it VF right now, and I'm calling this VI. So let's go ahead and do that with the conservation of energy. So we're going to go ahead for part one and say EI is equal to EF. Energy at the top is going to be all height energy, which is potential. And energy at the bottom is all going to be moving energy, right? Because right here they are moving downwards. So this is all going to be kinetic, right? And so that's how I did that. Now, if you're not sure on what types of energy are at each location, you could write both, right? But you would see that the kinetic energy would be zero because of this velocity, and because this height is zero, that this would be a potential energy of zero. How can I set that as zero if this is underneath it? I can call anything I want zero. So this can be zero. That just means that this is a negative height. All right, or negative position. Okay, so let's go ahead and come back down here and say PE initial is equal to MGH initial. KEF is equal to 1/2 MVF squared. What can I get rid of there? Hopefully you remember looking at this, something on both sides that doesn't need to be there. I mean, we can plug it in, but we don't have to. Mass. All right, and that's just nice to do, and it's fun to cancel things out. All right, so then we can go ahead and rewrite what's left. G is going to be 9.81. I'm going to go ahead and plug numbers in right away just because I think it makes it easier. Initial height. Once again, we're calling the water zero, so this is going to be 3 meters, right? And the person is initially 3 meters above zero. Final velocity is what we want to know, and that's when the person enters the water. Notice here, okay, I think we're fine. I was going to add something in, but this G is not going to be negative here because energy is not negative, right? Energy is a scalar. It's not a vector. So I'm okay with leaving that as 9.81. If, I guess another way, I think we're fine there. I was going to say another way to think of it would be that if this is negative, then the change in position would be negative, and so both these would cancel. That would also work because we did call down negative. So I guess if you're super, like, oh no, down has to be negative, well then that would be negative, that would be negative. But let's keep the energy positive there, and I think it'll be fine. We'll add the negative sign at the very end, and we'll see that come in. All right, so we'll multiply both sides by 2. Moves that 2 over there. 2 times 3 is 6. This is meters. All right, 6 times 9.81 is about 6 times 10, but let's go ahead and plug it in the calculator. It's giving us 58.86. Units, meters times meters is meters squared over seconds squared, which makes sense because we have to square root this, right? So we'll go ahead and take the square root, or the radical, of 58.86, and that gives us 7.67. Now, you might say, well, is it positive or negative, right? When you square root something or radical something, it can be positive or negative, right? So we have to accept one of the answers throughout the other. And so here we're going to go ahead and take the negative answer because the person is moving downwards, right? So this is for the first part. This will allow me to see while the person enters the water with a negative velocity or a velocity pointed downwards. So that negative 0.67 or negative 7.67 is that velocity right there. All right, now our final velocity from the first part, from the dive or the fall through the air, is then going to be the initial velocity in the next part, is what I'm trying to say. All right, so let's look at that, right? So in the next part, we know there's a force upwards. We know that there's an initial velocity, that negative 7.67, and we know there's a final velocity of 0 over this time period. So now we can use the impulse momentum theorem, right? And that is that force times time, or impulse, right? I can start from here. J is equal to delta P. And so F times T equals PF minus PI. You can see there's a lot of ways to write the impulse momentum theorem. So then therefore I can expand this out a little bit further. F times T is equal to MVF minus MVI. All right, and then we can go ahead and we want to know what's this force on the person directed upwards. So we think it's going to be a positive force. It should be positive, right? Because it's upwards. We'll see though if it is. All right, we want to know what it is. We know the time period is 0.55 seconds. We know the mass is 82 kilograms. We know the final velocity is going to be this 0, right? They're going to enter with a negative velocity. This will be our initial velocity. So the final velocity from part 1 is the initial velocity in part 2. All right, so the final velocity is going to be 0 because they're going to come to rest in the water. And we're going to subtract, we've got to watch our signs here, 82 kilograms again, times the initial velocity, which is that negative, right, because it's downwards, 7.67 meters per second. Oh, I'm running out of room. Okay, so we have a negative times a negative, which is going to give us a positive, and that's really important because we were looking for a positive force. We thought it would be an upwards force from the water. So I'm going to go ahead and multiply those two. So times 82 is roughly going to give me 629.11. 82 times 0 is just going to be 0 for this. All right, but this is going to be that 629.11. Units are kilograms times meters per second. Just go ahead and smash them all together, get that. All right, is equal to F times 0.55 seconds. It's hard to read with the 5s and the seconds. But you can see now what we just need to do to wrap this up. Let's divide by that. Let's get rid of that. Send the seconds over with it. This seconds gets to stay down here and join this seconds. So we're going to end up with seconds squared there. That's how that works with this on top, right, and no fraction on bottom or anything. So we're doing funky stuff there with dividing by or multiplying by the reciprocal. Sorry. So anyways, I'm gonna go rewrite now. F is equal to what's 629.11 divided by 0.55. 1143.83. Kilograms meters per second squared. All right, and what is this unit really? You should know this as units of force. That is a Newton. And we can tell from the sign that this is directed upwards. All right, and this is the net force that the person experiences to slow to a stop. All right, so that's it. If there's any questions, let me know. And definitely a challenge problem right there, and so I wanted to make a quick video. All right, have a good day.